So I'm going to combine two different series into one post here. And so got my spectacles on. We're going to talk about how to read research while at the same time doing a bit more of a deep dive into causal inference. And this is tangential to some of the series some of the videos that I've done on causal machine learning in the applied world. In this video, not only do I want to teach you how to read research, and this is a fairly complicated research paper to read and understand. It's dense, there's a lot of math, and you really need to understand the math in order to understand the paper itself. This paper is very similar to what you would see in some of the earlier days of machine learning, where we spent a whole lot more time and were a whole lot more mathematically rigorous because we had to support the usage of particular models, not incremental changes. We had to support the model itself. We had to support model selection criteria. And so the papers back in the early 2010s, early 2010s were far more mathematically thorough than they are now. Because like I said, there was a whole lot more to support. There was a whole lot more to prove. And when we talk about causal, especially causal inference, when it's applied to a real world situation, you're going to find exactly the same thing, especially when we were not specifically involved in an experiment and when we were not the ones administering an intervention or controlling the settings under which an experiment happened. This is very much what we do in the machine learning world when we are presented with a data set and we want to do some sort of causal analysis. And what this paper is going to bring up is a lot of what I've talked about in previous videos, that we can do causal inference, we can do causal modeling. However, what we end up finding has significant limitations in almost every case. And reviewing what others have done in this particular instance provides unique insight into how different approaches can coexist and different approaches can be completely valid, and comparing different approaches against each other can reveal some unique insights, possibly combining approaches. At the same time, I'll be talking a lot about causal inference. I'll also be explaining how to read this paper. Like I said, this is dense. This is going to be one of the more difficult papers that you will encounter because it is so rigorous and the math is so essential to understanding this paper. So let me dive right in. So what is this paper talking about? And again, in the earlier posts that I spoke about reviewing who your authors are, making sure your authors are from credible backgrounds, related backgrounds to the field. And in this case, you're looking at math-heavy backgrounds. You're looking at people who are experts on the math side. So you can, again, suspend a level of disbelief. You can have a level of trust in this paper. However, because this is such a complex concept and because this is in some ways contradictory to prior works, you're going to have to sort of come back to this level of skepticism and read this paper with a very thorough mind. So this is, like I said, going to be one of the more complex papers that you may encounter. However, I don't want something like this to intimidate you. It shouldn't. There will be areas that you don't understand fully. There's math in here. Most of it's fairly simple. I'll be completely honest. It looks complicated and scary. It goes into derivations and proofs. However, none of that is really that scary. And I should have turned my phone off. I really apologize for that. Like I said, none of this is really that scary. It's simple math, but it is so dense that it can be overwhelming, especially if you're early on in your career. So what do you do when you get one of these papers that is extraordinarily complex? Well, I'm going to walk you through that while also explaining sort of in the real world what causal machine learning looks like. And we have the abstract here. In this case, it isn't actually labeled abstract like it was in the last one, but you can tell. So this paper is focused on sort of causal inference in epidemics, specifically on mobility. So how able was a population to move around? How mobile was that population? And how does mobility, their specific metric for mobility. How mobile was a population? How much did they move around? How does that lead to, and in this specific paper that they're looking at the effects on deaths. So it's simple, right? We've got on one side mobility, this concept of mobility, and I hope I've explained that well. And on the other side, we have deaths. How many people died from COVID, or how many fewer people died from COVID based on mobility, and doing some predictions and doing some recommendations based on the relationship that they found in the data that they have access to. And this is historical data. This isn't this isn't an experiment, again, that they were able to do themselves and control. This is based on data that they were able to gather, and they're doing a causal analysis between mobility and your increase or decrease in deaths. They're doing causal inference as a way of recommending policy, and that's a lot of the reason why you'll see in academia causal inference completed on a data set, is to support a policy recommendation. So that's a common use case. And you've heard me talk about that in business as well. In my last couple of videos, I talked about making a policy recommendation for marketing and targeting a specific segment of marketing, having, and those individuals, those potential customers, having very, very particular characteristics. This is very similar, but it has to do with COVID, the epidemic, and social mobility. And so as they go through this introduction, we've talked about this before, they're reviewing what's been done. They're also reviewing the subject matter around their particular work and the experiment. They are, in this case, using a different approach to this problem, which is this marginal structural model. And so what they're going to do here is compare their marginal structural model to that SIR, susceptible, infected, recovered model. Now, other papers have done similar work. What they talk about in the introduction is how their paper produces similar results to some external papers, but is a contrast in approach to others. And for causal modeling, you'll find this very frequently, because one of the approaches that they contrast with is a machine learning approach. What they're essentially coming out and saying is that the machine learning approach isn't invalid. It is not flawed in a fundamental way. However, they see gaps and opportunities for them to do work using a different type of model and using a different approach. And I've talked about this, how machine learning isn't perfect. However, it produces good results. Those results have some drawbacks, and causal inference in many cases can do more than a typical machine learning approach can. It can be more rigorous, it can be better supported, and especially when you're talking about policy recommendations, using a causal approach may produce better results than a pure machine learning approach from an explainability and from an evidentiary support perspective. And so that's what they go through in the introduction. What I want to bring up here is something that I often have to bring up in my presentations and in supporting any of my conclusions. And that is, we don't always have enough data. And in many cases, there's no way for us to gather. We don't have access to the system. You hear me saying this a lot. I don't have the access that I want to the system. So the data that I can reliably gather is limited. And they do an exceptionally good job in this paper of explaining that. The data has limitations, and I've talked about this in posts that I do frequently. Data has limitations, and before I use data, I, as a data scientist, have to call out the limitations of the data that's available to me and explain maybe why I didn't use more plentiful data sources. Why didn't I go with more robust, more full data sets? Well, and it's often because those data sets have limitations. And as I explore, I talked about a lot of this during the very earlier videos about causal inference. As I'm exploring data sets, I find them to be incomplete. I find them to be interesting. They may lead to some interesting support for hypotheses that I have. However, they have limitations. And so when I do an experiment, when I actually go through and do the experiment, the amount of data that I can use is often limited because I need to use the highest quality data possible. And we're going to get into later on in this paper where they support why they're using this very, very limited, very targeted data set from the states rather than using national, international, county level, or any of the other available data sets that they had. Now, related work, I glossed over this a little bit earlier on, but they compare and contrast their work, their findings with other works and other findings. And they're very careful here, which is excellent. And you've heard me be very careful when I talk about causal inference. I talk about how there are benefits to my approach. However, there are also drawbacks to my approach. When you are reading a paper like this, which is very thoroughly written, you'll see that comparison. And oftentimes the authors will be very careful to say, our approach has benefits. However, there are also merits to other approaches that different researchers have taken. And so they are contributing to the body of knowledge by sharing their conclusions, and their conclusions are novel. Their approach is novel, but they're also saying that their conclusions support other works. And so they've come to very similar conclusions to other papers. And you're in your related works section, in a very thorough related works section, instead of simply doing a literary review, they are also comparing and contrasting their work to the work of others and calling out similarities and differences. Now, your paper outline, fairly straightforward. Here is the outline of what's contained in each one of the sections. You have a data review, and this is where it begins. This is where the depth of understanding begins, because what you're going to see here is, as I said, some of the justification for the data that they used, a deeper explanation for the types of data that they used, and now we begin to transform it from this simple data set to the mathematical terminology that they will use throughout this paper to describe the data that they're using. And this is a very important portion of the paper to read and to understand, but don't get intimidated by it. This is simply mathematical notation that explains the data. You've got a couple of figures to visualize. In my opinion, these are a bit difficult to digest. However, for an academic paper, this is surprisingly useful. Some academic papers assume an extraordinarily high level of competence for their users. And so the fact that they've included useful visualizations, while not perfect, this is rare, and say thank you, because in some cases you don't get that level of visualization. Now we dive more deeply into the math. And again, we have the representations of the data from above. So don't get too scared by that. But now we come into definitions. Now we come into what they say, considering a causal question. And in causal machine learning, this is one of the fundamentals that differs from your more traditional machine learning. Causal inference looks at the problem space first and does a deep examination of the problem space independent of the data. It allows the problem space to dictate what data needs to be gathered and what the constraints and requirements on the experiment are. That's very different from machine learning, where we start with the data and then potentially go down a different path based on the data. In this case, we cannot allow the data to build our hypothesis for us, where in machine learning, that's often what we do. It's often what I do. I will look at the data. The data will inform a hypothesis, usually a lot of different hypotheses. And then I will have to explore each one of those hypotheses using new data, using something totally different, because otherwise I'm using the data to support the data. And that's something that this approach prevents from happening. It's far more rigorous in the very beginning of the process. And I talked about this with causal machine learning in that, or causal inference and causal machine learning, in that the very beginning of the process is where the heavy lifting happens. You're doing a whole lot more work and an extraordinarily deeper and more rigorous evaluation before you even get to the data, before you even get to doing the experiment. Now, what are they going to do here? They are explaining their approach to causal inference. And if you don't understand what you're reading, and in many cases you'll get to this and say, this is simple math. However, you may be at an early stage in your career. You may be using papers like this to learn and to advance your knowledge within a particular space in the field. And so what does all this mean? This is, potentially confusing to you. Whereas this is, to someone like me, I'm looking at this and it's fairly simple and straightforward. The text in front of much of the math is going to help you to understand what it is that you would need to search for to begin to understand their equations. Many times in these papers, they will give you exactly what it is that you need to Google if you are unfamiliar with the mathematical concepts. Don't feel bad. I had to Google several things to remind myself of all the math that they're using. This is dense and complex, and it gets even more dense and complex as we go down through the paper. Now, you're going to ask yourself, why is there so much math in this paper? And I alluded to it earlier. They are proposing an approach using causal inference, which needs to be very, very well supported, especially from a model selection perspective. And that is what they are doing in these further sections, is they are explaining and proving and supporting their approach using a very rigorous mathematical explanation, or mathematic explanation. I may have used the wrong terminology there. And again, you have a wonderful, and this is something that you often get in these papers, is they understand that there will be a variety of audiences thanks to the reviewers of the paper being from a variety of different backgrounds. So there will be reviewers who say, I don't see the support for this, I don't see the explanation for this. And their questions will, in the end, provide a whole lot more information in different formats for you potentially having a different background. Because as you can see, if you've got a strong math stats background, this is not confusing. If you do not have a strong math stats background, this might as well be some Martian language. Now, what would we do to understand this? And again, you have this wonderful explanation and write-up of what each one of these different variable concepts, and they've gone beyond just explaining variables to explaining variables in a conceptual manner and explaining each one of these elements in a conceptual manner. And they've done a very, very good job of this. And so papers like this are excellent opportunities, and you should really look for papers that do thorough explanations, both mathematically and in plain language, of what they are doing and how they're doing it. If you've taken an applied mathematics class or perhaps a physics class, you've seen entire lectures like this, where a professor will go through the steps of a proof and explain how they got there. And that's what you're seeing here. If you need, and I've talked about this in the last post about reading research papers, if you need more background, there are all of these wonderful background sources that you can go into to really understand all of the concepts that are being presented here. You notice they do a very good job of explaining how this is what we did. However, this is another approach that someone else may have more effective, may be a better choice. And so here's another way that you could potentially do this. And you can, again, go in and research each one of these. You can begin to understand in more detail what a marginal structure model is. You can look at, and this should be fairly familiar to you, your parametric, non-parametric, semi-parametric model concepts. So you can look at what are those. You can look at your G computation. Those are things that you can Google. And if you're having a hard time sort of getting a grasp on all of these concepts, you can Google that and you will get a better description, a better explanation of the math by looking at the background papers and by Googling the fundamental concepts, which they will, in plain language, also explain to you. What gets hard is as you go down this paper, each concept builds upon all of these other concepts behind it. So the further down the paper you go, the more confusing this can get. But that's okay. You're going to spend a lot of time on a paper like this. You could spend days on a paper like this, getting all the background information you need to understand what it is that they do. Why would you do that? For someone like me, I'm learning quite a bit about what process they're using and beginning to look at my process for doing very similar things and saying, okay, it's interesting. They have a different approach potentially than I do. In this case, this actually lines up really well with a lot of the work that I've done process-wise in causal inference and applying it to machine learning. And they have a lot of the same ideas I do about the benefits of causal inference versus machine learning for informing actions, for being for prescriptive types of inference, where I'm going to make a recommendation and then having to support it rigorously. Am I going to present this math to the C-suite? No. That would be an absolutely horrible idea. However, I am going to well support internally my experiment. I'm going to internally well support my approach, my model selection, and my conclusions and my results. And so if I were to have a review board, a peer review board, I would need to go into something similar to this level of depth. Now, I talk about this a lot. In the academic world, there's a deeper level of rigor, a higher level of proof required in order to do an experiment. What they've done here is far more rigorous than what I would have to do to support running an experiment. So I have a lower burden of proof to just say, I want to run this experiment. I think I have enough evidence to run this experiment, and I think I've designed the experiment rigorously. Now, there will be the same level of review on how I've built my experiment and how I'm planning to execute my experiment. And typically, the first, second, third, fourth version of my experiment in a peer review board is rejected. It is not thorough. I haven't thought everything through. I've sort of let the data lead me by the nose in many cases. And a review board, the purpose of having a review board is to have others put their eyes on this and say, okay, here's what you haven't thought of. And in many cases, you bring up things like confounders, counterfactuals. You bring up sensitivity and uncertainty that I haven't taken into account. That's usually what happens in an experimental peer review, is a whole bunch of heads get together and they see the things I haven't because they are removed from all of the assumptions that I've made. And this is why it's so critical to detail assumptions in the same way that this paper is detailed assumptions. It's so that the review board can look at my experiment, my proposed experiment, and shred it and attack it from every angle possible until this is the best experiment possible. And again, that's the lower bar of proof. It doesn't have to be a perfect experiment. It has to be the best experiment possible. And then knowing the flaws, knowing the holes in the experiment, which In this case, the authors do a great job of detailing. They very well support their experimental design and their choice for data and so on. However, they also admit that there are flaws and that this could be done in a perfect world better, maybe using a different approach. And so a lot of what you're seeing here is supporting their approach on the one hand, but also acknowledging the limitations of their approach and detailing other alternative approaches which may have been equally effective and which other researchers may want to explore. And again, the reason why this math becomes so dense and in many cases so confusing is because, like I said, you're building concept on concept on concept on concept. So as soon as you encounter a concept you do not understand, get to Google and understand it. Get into it. Spend as much time as required for you to understand that concept because it's going to keep getting used. And if you don't understand it, everything afterwards gets very, very difficult to follow. In a paper like this, I talked about in the last paper, you can gloss over a lot of the math. In a paper like this, you can't. You need to understand the support for why they did what they did if you ever want to reproduce this type of a process and understand this type of a process. So while in many machine learning papers that are recent, you can gloss over the math to a certain extent and still get the fundamental concepts of the paper. When you're talking about an emerging field, that crossover between machine learning and causal inference and understanding how you would create the experiment and support your work and so on, from a process standpoint, you need to understand this math at a strong enough level that you can follow the paper and understand how they supported and proved out their approach. Now they're detailing the models themselves here. And again, this is sort of back to older machine learning papers. We did this, well, they did this a lot, where there was a deep level of support for their model selection. And in many cases, they had to explain why they selected one model when there was a more traditional approach that was commonly used by others. And this is where you can, in many cases, see in some of the older papers, all of what we use today sort of emerging out and being proven out, and the things we take for granted in machine learning today, the approaches that we just say, well, of course, that's obvious. A lot of those are obvious only because they were rigorously proven out by the research that we basically take for granted today. And that's what you're seeing here is a lot of the justification for their model selection and a lot of the proof for the end approach that they took. And so, and like I said, this is not really that complicated from a mathematical standpoint. However, if you're unfamiliar with the concepts, it's simply going to be something that you have to Google. And remember, all of this text is going to explain to you not only the variable concepts, not just the variables, the variable concepts. And those concepts may be something that you need to Google. So again, rolling through their very thorough treatment and explanation of their approach, model selection, how they decided to select parameters in some cases, how they decided to add in these variable concepts, what it is that informed their decisions, what results came back into iterations of this model and this approach that they've used. And so, like I said, you can see this is thorough and more thorough than you are used to. Counterfactuals. I'll get into this in a subsequent video because counterfactuals are one of the core concepts of causal inference, and it's a complicated concept. It is evolved. It's evolved quite a bit since the 70s, and subsequent authors have varying approaches on counterfactuals, all of which are well supported, all of which are very difficult to apply to machine learning cases. But there are some approaches that you can use, and like I said, I'll cover that in another video because this is dense, and understanding the background behind counterfactuals is one of the very important things that you need to do in order to understand causal inference. So I'm going to gloss over this just a skosh, even though it's a small section that's very, very important. Now, fitting, this is pretty well established. You understand fitting. You understand semi-parametric models, stabilization. You understand this. So I'm going to gloss over this quite a bit from a conceptual standpoint because this is more, this falls in line more with what you're used to in machine learning. It's definitely applied differently, but conceptually you can follow this pretty easily if you have a background in machine learning, at least a little bit of a depth of understanding in machine learning. Again, if you don't, do the background research. And there's papers to support. There are a number of terms in here that you can Google if you've never heard them before, and they'll take you down sort of the rabbit hole to understand a lot of what's being done here and in some of the subsequent sections. So scrolling through, and yeah, like I said, most of this is familiar. However, if some of this notation seems difficult, use Google. We all do. I had to. So don't feel bad about using Google. Now results, we've talked about the results in a previous video for reading research and how important it is to go through this thoroughly, to understand the results and to evaluate for yourself how well you trust your ability to implement something like this. The results are going to give you an idea of how ready for prime time this particular paper is. Now, in this case, there's no code associated with this paper, and there really shouldn't be. This isn't a machine learning paper, so you're not going to get code in many cases with a paper like this. However, you can review the results from a process standpoint, and the results are supporting not only their findings, but also their approach. They're supporting the rigor of their approach and explaining why this approach leads to a recommendation, a prescription, which is better supported. They are also explaining the, sensitivity analysis, very well. Again, I can gloss over this. They're explaining what else they considered, what other approaches that they looked at, and why they chose the one that they did, but also why there are other approaches which may be equally or more effective. And this is a rigorous interpretation of the results. And especially through the sensitivity analysis, they're explaining what else could play into the model, what else could play into the results, and what are the limitations. Their sensitivity analysis reveals some interesting limitations to their work. Not only do they acknowledge that the data itself is, it's a pretty small data set, it's a pretty small sample size. They still get interesting results because they do such detailed analysis and experiment, but their sensitivity analysis shows that there are still limitations to the causal relationship that they are drawing between different levels of mobility. And it's up here, actually. I went over it a little too fast, but there are well-supported assertions. However, there are limitations to the assertions that they're making in this paper, and they do a very good job of calling those limitations out in their analysis of their results and their deep, deep treatment and explanation of their assumptions. And for causal machine learning, that's hugely important, to call out your assumptions and to explain things like confounders, what confounders could be in there. And when I talked about my personal experiment working with that luxury brand, I called out a confounder, which, in that case, I didn't resolve. I wasn't able to do a full exploration and resolve the impact of that confounder on my recommendations, on the policy about marketing that I was recommending. And they do something very similar here, where they explain, again, limitations of the causal relationship that they have effectively supported. And that's what a lot of this section is not only discussing their results, but also calling out the limitations of those results, of them saying that obviously there's a strong tie between mobility and deaths, both deaths increasing and deaths decreasing. They call out in a very thorough way the impacts of the progression of the pandemic on their results. That obviously, as hospitals get better at treating patients, you're going to have fewer deaths, and that plays a role. You are going to have higher levels of vigilance and lower levels of vigilance, which is another approach. And that's something they call out and say, here is the impact of vigilance versus mobility. They are explaining a lot of these other variables and other factors that are going to come into play to explain some of why they chose the data sets that they did, and they chose the approach that they did, and what are the limitations based on this very, very thorough review of not only the data, the experiment, but also their conclusions and the impact that other approaches may have had in changing their conclusions that are worth exploring, that are worth having other people do going forward to understand this causal relationship much better, and to also maybe find other causal relationships, find other factors that would make this policy recommendation about mobility and about increased vigilance in other pandemics, in future pandemics, more effective, and to be able to get those out earlier on. And so that's really what this work is providing, is an alternative method to create policy recommendations, to prescribe actions, and it's very thoroughly supported. Now, I've kind of crossed two different topics over each other, and I hope I've done it in a semi-interesting way. And I hope from a causal, if you're coming into this from the causal series, I hope I've explained a bit more of causal in the academic and sort of the more rigorous causal inference and how researchers support their prescriptions and policy recommendations, while also explaining a little bit about what my process derives from when it comes to causal machine learning, and where a lot of sort of I have more leeway versus them in the experiment side and just justifying doing the experiment. However, I have many of the same requirements when it comes to supporting the prescriptive action. In this case, it was the marketing that I proposed to be done. How I also at that point come back to having a very high level of proof required for me to recommend a particular action, for me to get them to spend. I hope I've also explained a bit of how to read a very complicated paper, how to go in and Google different pieces of math where, it's hard to Google math, but you can Google some of the concepts under the math and find explanations, not only in the supporting papers, but also by doing quick searches on some of the key terms that you see when the math itself is explained or the approach itself is explained. And I hope I've helped you understand how variable concepts are defined and how you have to sort of follow the chain. You may even have to take some notes that you refer back to understand how each concept is layered on top of each other. So this has been a long video. I hope you've stuck with it the whole way. I hope this has given you a better understanding of not only how to read a research paper, but also about causal inference, causal modeling. Thank you for sticking with a very, very dense video.